All right, I'm not sure how well this is going to work because I don't have any students in class today. And I still want to cover the three sections of Chapter 5 and today and Friday, so you all can do an exam on Chapters 3, 4, and 5. So I'm going to go ahead and cover, I'm at least going to take a shot at covering Chapter 5, Sections 1 and 2. This is and then we can cover 5-3 on Friday if anyone's here. We're looking at now, what we're getting into in Chapter 5, it's called discrete probability distributions. It's going to be important that you remember the difference between classical probability and empirical probability, because they're going to become very germane now. First thing we got to deal with is the definition of a random variable. And the book defines a random variable as a variable whose value is determined by chance. Well, I have this was not real fond of this approach, this way of thinking about it. I'm also a physicist. I teach physics, and I know that we live in a universe that is governed relentlessly by causality. That nothing happens that is not caused to happen. We don't always understand what causes it. We certainly cannot always predict outcomes. And so we invent this notion of randomness to deal with it mathematically. We talk about the flipping of a coin or the tossing of rolling of a die as being a chance event. Well, there's nothing chance about it. The coin's motion, its angular momentum, its rotational motion, its translational motion, is all fully determined the instant that it leaves your thumb. The moment that coin loses contact with your thumbnail, its motion is determined. Now, chaos theory teaches us that, or it explains for us that even though its motion is still fully governed and is still fully and wholly deterministic, that doesn't mean that we can predict it, because the resultant motion is so hypersensitive to all of its initial conditions that we can't possibly know or measure them all to sufficient precision to make a meaningful prediction. And so we basically treat the outcome as chance. And this is where we get this notion. Point of fact, I personally prefer defining randomness as the ratio of the information dimension of a set to the capacity dimension of the space it occupies. We talked about sample space, set of all possible outcomes. And we talked about events as being a particular set of those outcomes, one or more than one. Um, well, in chaos theory, you can calculate values or quantities that are known as the dimensionalities of those sets. The information dimension of the set of outcomes is a measure of how much information is contained in that set. And the capacity dimension of the sample space, the space it occupies, is a measure of the maximum amount of information that could be contained in that set. And so I like to define randomness as the ratio of those two dimensions. It has the advantage of applying not only an integral, integer numbered dimensional spaces, but it actually extends into any space with any real number of dimensions. So it would extend into fractal spaces as well as n-dimensional space we normally think of. It also, when you use that definition, it also has it also subsumes what what statisticians would call chi-square. But you know what? That's all interesting, but it's not what we're here for today. We're going to go ahead and pretend like there is such a thing as a chance event, and we're just going to define it as an event that we are not capable of predicting. And therefore, we can talk about a random variable being a variable whose value is determined by chance. And then a discrete probability distribution is then defined as the values of a random variable that a random variable can assume and the corresponding probabilities of those values. Those values can be determined theoretically or they can be determined empirically by observation. I told you that was going to be important. Let's work through an example here. Example 5.1, page 267. Rolling a die. Construct a probability distribution for rolling a single die. Well, the sample space is 6. You can have an outcome of 1, 2, 3, 4, 5, or 6. That is the sample space of rolling a single die. Now, the probability, since rolling a die is considered a chance event, then the classical probability would define that there is an equal probability that any one of those events could occur. So the probability that 1 is the outcome would be 1 in 6. The probability of 2 being the outcome would be 1 in 6, and so forth. And that is a discrete probability distribution for rolling a single die. Let's take this and let's do example 5.2, tossing coins. Represent graphically the probability distribution for the sample space for tossing 3 coins. Okay. Go over here. going to talk about the probability of tossing 3 coins and getting a heads. So, if you toss 3 coins, it's possible that they will all be tails. You will get no heads. It's possible that you will get 1 head and 2 tails. It's possible you'll get 2 heads and 1 tail, and it's possible that you'll get 3 heads and no tails. Well, what is the probability that you'll get 0 heads? Well, that means you're getting 3 tails, so the probability of getting 3 tails is 1 chance in 2 times 1 chance in 2 times 1 chance in 2. Or 1 chance in 8 that you will get all 3 tails. So the probability of getting 0 heads is 1 chance in 8. Now, what's the probability that you will get 1 and only 1 head? Well, the probability that you'll get the head the first time is 1 in 2. Remember your counting rules. Now we're looking for the probability of getting a second head, which is independent of the probability of getting the first head. And then we're looking at the probability of getting a third head. So the probability of getting all 3 heads, 3/8. I'm doing this wrong. Probability of getting only 1 head is the probability of getting one tail. Probability of getting 1 head is 3/8. Easiest way to do this is just to construct our entire space. You get tail, 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 head, tail, head, tail, tail, head, 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 tail, tail. I'm running out of space here. Boy, this is, I don't mind telling you, this is hard to do when there's no one here that I'm talking to. So, yeah, this is just unbelievably, incredibly awkward. Okay. There are 8 possible outcomes. I don't know if I even want to. I mean, seriously. Yes, I am actually thinking now. I'm deciding whether I want to push on and do this or not. One, two, three, 4, 5, 6, 7, 8 possible outcomes, 8 permutations of tossing 3 coins. Only one of them has no heads. This one has 2 heads. This one has 2 heads. This one has 1 head. This one has 2 heads. This one has 1 head. This one has 1 head. And this one has no heads. I'm sorry, this one has 3 heads. So, there is only one way to get 0 heads, 1 in 8 chances of getting 0 heads. How many ways are there to get 2 heads? 1, 2, 3. There are 3 ways in 8 of getting 2 heads. There's 3 ways in 8 of getting 1 head. And I just wrote these backwards, or I counted them backwards, but they work out the same. And there's only 1 way of getting 3 heads. This is a discrete distribution for tossing a coin and getting heads. So if we draw it graphically, there's 0, 1, 2, and 3 heads, 1/8, 2/8, 3/8, 4/8. So that would be 1/2. And there is your graphical representation of your discrete probability distribution based on classical, hey, keep up. Over here, you. Follow me. So that's our discrete probability distribution graphically represented based on classical probabilities. Next one they look at is the probability distribution winners. The Baseball World Series is played by the winner of the National League and that of the American League. The first team to win 4 games wins the World Series. So, in other words, the series will consist of 4 to 7 games depending on the individual victories. The data shown consist of 40 World Series events, the number of games played in each series represented by the variable x, and the probability p of x for each x. Okay, this would be empirical probabilities. There is no, ideally, in fact, it's hopefully it is not just random chance that one team will win. It would sort of defeat the purpose of making it a contest. Look here at the raw data, we've got X being the number of games played in a World Series, 4, 5, 6, and 7. And the number of series, there were 8, 7, 9, and 16. Now this is saying is that 8 times in these 40 years of World Series, 8 times the series was won in only 4 games. Only 8 times was it a sweep by one team or the other. 7 times it was the series ended in 5 games. 9 times it took 6 games to win, and 16 out of 40 times it took a full 7 games of the series to find a victor. Let's add these up and make sure. We've got 9 and 8 is 17, 24, 30, 40. So yep, we got 40 years of data here. So let's look at the P of X. This is the probability of X I'm going to do something a little different. Let's say probability of 0, 1, 2, 3, 4, 5, 6, and 7. One of the definitions of probabilities, keep up with me, little swivel. One of the definitions we talked about of probabilities has to do with that the probability has to be a number between 0 and 1 inclusively, where if it's 0, that means there is no possible chance for an event to happen. If it is unity, if it's 1, then that is an absolute certainty that an event will happen. Well, what is the possibility of the series being won in only 3 games? 0. There is 0 possibility, which means 0 probability, that a team can win the World Series by winning only 3 games. The winner has to win 4 games. If you don't win 4 games, you didn't win the series. So there's 0 probability. It could be 3, 2, 1, and obviously 0. We could actually continue that on ad infinitum. We could also say, what are the probabilities of 8, 9, 10 games being required to win the World Series? Well, they don't allow them to end in a tie. They will keep playing until the next day, until somebody wins the game before it's considered a game. So since there are no ties, they can never have to play more than 7 games. So the probability of playing 8, 9, 10, or however many more you want to count is all probability of 0. So That means every World Series that is ever played will, by definition, consist of either 4, 5, 6, or 7 games. Now, in this case, what is the probability that the series ended in 4 games? It was 8 chances in 40. Which equals 0.2. Or how many zeros are they adding here? They're adding 3 of them. Yeah. 3 digits. So there are 0.2 is the probability that the series ended in 4 games. And probability of 5 games is actually less, 7 in 40. 0.175, if I remember. Yep, yeah, again, don't trust me to do arithmetic in my head. 6 gives us 0.225. So 9 out of 40 is 0.225, and 16 out of 40 gives us 0.400. Does this add to 1? 5 and 5 is 10, put down the 0, carry 1, 7, 8, 9, plus 1 is 10, 0, carry 1, 2, 3, 4, 5, 6, plus 4 is 10. The probability that the series will consist of 4, 5, 6, or 7 games is 100% certain. So, let's see, here's 0.25, so we'll say that's 0.2. 5 actually only went to a 0.175. 6 went to 0.225, if I'm not mistaken. It would be a little bit above here. And 7 went all the way up to 0.4, which would be right about in here. And there is your empirically determined discrete probability distribution for the number of games necessary to win a World Series. Does this look anything like, does this graphical distribution look anything like this graphical distribution? It does not. This is very centrally dominant and well-centered. In fact, if you were to extend it out to a continuous distribution, it would be very bell-shaped, or what we call a normal distribution. This is U-shaped. And let's back up and look. What did they call these different shapes of distributions? I can find it real quick. That far back. There it is. This one actually looks kind of U-shaped. Right? It would not be J-shaped because and I don't know if you'd call it bimodal because the modes are, we don't know where the modes would be. Well, the modes can't be any lower or higher than that. But point is, it's not a normal distribution. It's a U-shaped distribution. Why is that important? Why am I emphasizing that? I want to make sure that you pay attention and notice this. Because what is our purpose in learning all of this? We want to eventually we want to not only be able to describe data distributions like this, we want to be able to make inferences about them. Remember, two purposes of statistics. There is descriptive and inferential. And we want to, at some point, be able to talk with some quantifiable measure of certainty or confidence that we believe that we know within some degree of certainty that a parameter of a distribution is going to match this this particular statistic. We want to be able to say with some quantifiable certainty that the spread of this population distribution is no more than this much. And if you'll recall, even what we already learned in the measures of position and measures of variation, we talked about the Chebyshev rule, with what percentage of a distribution would be within so many standard deviations. And we found out that according to the Chebyshev rule, and that there were certain, we could say there's certain percentages of the population that are within a distribution for any distribution, no matter how it's shaped. But then, if you'll recall, when we talked about a normal distribution, which was a nice bell-shaped distribution that was very centered and everything was, there was where the mean, the median was all equal to the right there in the middle. Suddenly, those percentages went way up. It's like what, 95% of the population is going to be within 3 standard deviations of the mean for any general distribution, according to the Chebyshev rule. But when you have a normal distribution, that 95% goes up to 99.7% for 3 standard deviations from the mean. So you're going to find as we go forward in this course, we're going to pay a lot of attention in being able to look at descriptions of data and know whether we're looking at a normal distribution or an other bimodal or U-shaped or left J or right J. When we find that we can say with certainty that yes, this is a normal distribution, then we can make those inferences with significantly more precision than we could otherwise, and with significantly more confidence than we could otherwise. So we will pay some attention to whether or not distributions are normal. Drawing them out graphically is one way to look at it, and we've looked at the terms to describe the different shapes. We've also started seeing some of the ways we can look at just the numeric parameters of the numeric statistics of the sample to make determinations about how is it distributed. Is when the mean and the median and the mid-range and the mode are all the same value or are very close in value, then we know we have a very normal distribution. When the mean and the mode and the mid-range and the median, they are no longer nearly equal, then we know we have an abnormally distributed distribution. I think that's about all I'm going to cover today. If you're here on Friday, we will go through the variance and standard deviations, which is basically we're revisiting. As we've already looked at variance and standard deviations of populations and samples. Then we will cover the binomial distribution. And if you're here on Friday, then you will probably score very well on the take-home exam. And if you're not here on Friday, then 0 for an exam score is going to be a tough one to overcome. I will see you on Friday.